One, two, three. Otherwise, you are outside of the. Okay, thank you. Hello, everyone. My name's Lukasz Luba. I'm principal software engineer, currently tech lead at ARM, responsible for kernel development, some design reviews, and I would like to talk today about standards, in particular the energy meter that we would like to see in a common kernel. And this is the agenda. I'll start from the agenda, and the scope is not that huge, and hopefully that will go smoothly. As you can see, there is some success stories summary, the motivation for this new standard, some proposal how we can implement something which could be reused by other vendors, and yeah, hopefully for different architectures maybe as well. So let me start from the success stories. Last year, OSPM, I have presented some patch set and feature set for a dynamic energy model. It was consisting from 4 feature sets. 3 of them, they are already in mainline. The last one is currently under review. I'm going to send a patch soonish. The backporting is ongoing to the Android kernel. What has been done? There was some optimization for the hot path in the scheduler in the EAS. Chip binning was addressed, which was also quite good. And mainly the patch set was addressing a leakage problem, which I will discuss a bit as well. And there are some other results. You can find them as well on the list from real world workloads, such as Junk Bench or YouTube, where we can modify actually energy model to better align and fit better to the hardware, and then the workload can also benefit from that. So those are the success stories. So I hope this year OSPM would be as well fruitful. And this is the motivation for this new standard. We have actually diversity of SOCs, and we would like to actually standardize something which is kind of a basic thing, which is an energy meter. So because we don't fully control our vendors that can implement different firmware or different drivers, and there are existing interfaces in the kernel, but yeah, the specifics of a particular hardware or a device, this is not reusable easily for something like thermal or power cap, that I will explain a bit later. So it would be nice if we can agree on something which is a common and understood well by the maintainers or driver developers, so we can just reuse. Why we need this? Because that can provide better quality information for our algorithms. Let me introduce some information about the recent and modern processors, and I will also explain a bit more, because we have touched this topic yesterday, about the power and performance profile of the CPU that can vary. And as you can see on that plot, it's an abstract view of a processor, a quite modern processor. This is Cortex X4 documentation. There are 21 pipelines, and actually the modern processors, they are more aggressive and more sophisticated. They will also consume different power depending on the workload and depending on the surroundings which assist actually the pipelines. We also have some special features, microarchitectural features like memory tagging or some security extensions or some dedicated instructions, for instance, for cryptography or compression. They will also use different power than you normally can put into the energy model. So it's becoming more and more complex. And this is one of the recent CPU announced two days ago. It's called Cortex-X 925. It gets 2 more vector units. So instead of 4, we will get 6. More sophisticated prefetchers for the data, and more sophisticated branch predictors. All of this makes the hardware more complex and more dynamic, so less predictable. On the other hand, we also have some new mechanisms which are also publicly available for like 1 year now. You can read about them in the documentation. Those are the performance and power management features, and they can control actually the aggressiveness of the processor. They can control maximum power that can be used, but those are implementation defined. So the behavior of that mechanism for preventing something like thermal or power issue on the power rail, those will be implemented probably by the vendor when the final silicon would be designed and manufactured. So those 3 at the bottom, the MPMM, PDP, or dispatch block, those could be implemented differently by a different vendor actually. So configured differently. But the need is that we want to trace actually the power usage because we discuss the real power numbers before we actually send any parts that we do a lot of tests. Internally, we do the review of those results. So we have to justice the need of the new code or make some good decisions about the design. And here is some example how the power variation can look like at the same frequency. Depends on the type of the workload that you run. So it's heavily related to the instruction mix, but also due to the data type that it's used there. It depends if you use the scalar units or the vector units. It's also dependent on the data set size, if it's fitting the cache or if the cache is utilized by some other core as well, or due to the cache, due to the core footprint. So as you can see, this is one frequency only, so one OP, but the power will be very different. We currently have in the energy model 1 value, which is here for that particular Cortex-X1, 2.2 watts, and we try to use that value for power estimation from EAS hot path simulation point of view. But as you can see, we are not always right about the average power that we consume at OPP. That's why we run offline post-processing when we record a trace. And one of the first things that I have done when I got the Pixel phone, the Pixel 6, was to introduce actually the tracing for the energy meter. So you can record the data into the trace file, which was really helpful because that simplifies the validation of the proposed solutions. And we are talking about really tiny changes sometimes, like today morning, Hongyan was showing the results about some less than 2% differences when we are talking about some uClamp implementations. So we really need to find a good way how we can map the workload and the tests together with the power data. And the tracing is quite handy. As you can see, the power can be different. And that's why we want to have some kind of standardized way to trace not only on one particular phone, but on bit more phones. Yeah, as I have mentioned last year, the power can also depend on the temperature of the whole silicon. So it's called leakage. So the more power, the higher temperature is on the silicon, the higher power average you can consume on your CPU when you do the workload there. It also depends on the other CPUs on the same power rail, because as I have mentioned, some mitigation mechanisms might kick in to save the safety region of your voltage level. So you might get throttling just to be sure that the safety conditions are met to not put the power rail into some position that you cannot sustain the voltage there. So the throttling will kick in, and that's also affecting your power. So measuring the power is really important for us, and calculating energy as well. Here is some example about the performance that you can get from the same CPU, but running different micro benchmarks. Well, those are written by me, mainly in assembly. I call them power family. We can see from that plot that the capacity of the CPU is different. We have touched that topic yesterday a bit with on the talk from Intel. But as you can see here, the capacity difference can be even 4 times different, so 4x. And there might be soonish even wider differences. So we have to measure correctly the performance and the power, and then derive the energy that we actually use for certain workloads when we are proposing some improvements. Here is the slide that I borrow for the second time from Morten. That was the first trigger to show the audience that we can have different power and performance profiles. That's how I call them. It's basically, if you have this problem with the different performance, different type of workload, then you combine the power variation as well for them, then you can end up in such a situation that you have different power and performance plots. So on the x-axis, you can see the normalized performance. On the y-axis, you can see power. And those 4 are totally different, as you can see. We currently have one energy model, as you know, one-dimensional, how I call it. But we have to choose the right one in order to be quite correct in most of the cases. So we have to measure different workloads, and then we have to pick up some average value and store there. We can, from the few weeks back or maybe months, thanks to Rafael Merch, we can modify that in runtime. So if we realize that there is a huge need to override the older energy model with one of those new snapshots, then we can do this. But that's not the ultimate solution. We can also adjust for the leakage, which is actually making some issues for our energy estimation, especially for the thermal usage. But I will talk a bit later about this. Here is the plot that shows you might recall this because I showed this last year. The plot is showing on the time, on the x-axis, the time, actually 1 minute of tests. That test runs on one big CPU at fixed frequency, 1.4 gigahertz, and the GPU was used or not. So those are 2 examples. And then when the GPU is running some code and drains roughly 1.5 watt, then actually it heats up the whole silicon. And you can see in the time that this power would be a rising function. So it's not anymore the flat like on the top plot, it's impacted by this leakage. So the total power can be different. But fortunately, we can address that now. If a vendor has a module to recognize the situation and has some data from the past, then we can do this at runtime safely. But as you can see on this plot, there are some measurements, and those are measurements from this tracing. So the trace is actually capable of saying at each particular moment what was the energy usage or what was the power usage during that test. Some other useful things that they are there. We use also this energy model for estimating input power and output power for algorithm called intelligent power allocation. It has some closed feedback loop, and it can fix itself because that's a PID algorithm, but it cannot address all of the issues, and I will show you some of the examples. So this input power estimation, this is done purely based on the software currently. So we use energy model, and then we use utilization of the CPU. We make some assumption about the average frequency that was used, and then we estimate the power for the CPU. A similar thing is implemented inside the DTPM. Daniel has added energy model, and we try to be aligned to the one way of estimating the power of the CPU. But there are some subsystems which can help us actually, at least in those two use cases in the kernel. There are devices for the IIO or HWMON where you can get a physical measurement from the board if it's there. And if the driver is capable of doing this, then we might have some common interface to allow them to register to our need. So those two frameworks could use the real measurements that we could agree, and we can align for this power estimation. We also have, in our R implementation, there is a protocol SCMI, which talks to our reference firmware. We can have power numbers from there, from those chips which support actually our firmware. But this is not currently the ultimate solution because we cannot force the vendors to actually deploy our firmware. So they can have some legacy systems which they will just continue, but they can have those hardware meters or monitors. So we can just have like a common place to combine this and reuse in any system that we want in the kernel. And here is one of the example how much difference we can see in our world. So this test shows, that's Geekbench 5. It shows the power usage in time. So the power is the y-axis, and the x-axis, that's time. I'm talking about the bottom plot. There are other plots on the top. That's temperature on the y-axis. In the middle plot, there is a cooling state for the device for the big core. And this is basically a test which is running on the big core, roughly till this big spike where the multi-threaded test suite starts. So the first part is a single thread test. And then you can see actually 4 different plots on this bottom plot. Those are the power plots. Either they are estimated by our software, or they can be read out from physical meter. And as you can see, our current estimation for the power, for instance, on the first test, that's actually a cryptography test. And the real power, which is the red or the orange one plot, it's 2 times less than what we estimated using our software model. Then we have some big spike of the real power at the end. Also, we underestimate in this case. Then there are some other tests. One of the heavy tests is here, where we can actually see throttling kicks in because the cooling state in the middle plot, this is controlling the frequency and the voltage of the CPU. This is changing our performance, the performance and the frequency of the CPU. And as you can see, our software estimation method just assumes that the power is lower than 2 watts, while in the reality, the first spike is more than 3 watts, and then it decays slowly because we reduce the voltage. Some other tests, also some heavy mathematical operation, as you can see, a huge spike to around 3.5 watts, while we estimate 2.2 because that was the default energy model.
Just, Lukasz, one question. Yes. Can you describe which line is it? Which one is the energy model used, I would say, in the
yes.
kernel?
Yes. So apart from this, which is called input power from hardware, and the orange one. So the orange one, this is the proposal of my experimental energy meter inside the energy model. The red one is just a pure read from the IIO device. And then there's a blue plot, which is the software power estimation inside this new thermal CPU freak. And the green one, it's the old style. Old style, I call it old thermal because before we introduced the energy model, we had some local energy model which was accounting leakage. So there was static power and dynamic power in the old thermal model. So we could adjust based on the leakage, based on the situation, the leakage.
Okay, so the blue one is the one that we have in the main line.
Yes.
That's it.
Yes, and that okay. The green one was the past. So before some changes done with the.
Okay.
Yeah. So those are two.
So the blue is the current main line. The red is the reality. The orange or yellow is
kind of a proposal. Yes. And the green one was what was available not long time ago, before we switched to normal energy, but not modified in runtime. So we lose actually the capability to say about the leakage in runtime. But after this parsed from the last year presentation, we can actually go back more to the green state from the blue state of the situation. But as you can see, this is still not the ultimate solution. So you could adjust in some known workloads which can fit into the model, maybe like this one, the third one, or some of them in the middle. They are quite close to the reality, but not all of them, they can fit into this model. So that's why I'm asking for some common interface that you can plumb in the hardware meter. And the hardware meter will have some requirements that I will talk a bit later. But as you can see, what can happen if we don't properly estimate the power in our algorithm? It can fix itself, but those undershoots or overshoots in the power, they can cause some big spikes on the top plot, which is the temperature in time. As you can see, sometimes we cross the 100-degree threshold, which is quite dangerous for the normal silicon. We also throttle them hardly in that test. As you can see, the power wasn't that dramatic, enough that dramatic, but actually the situation is getting worse.
Lukasz.
Yes.
If you can,
go back.
It's not a question, but if you can briefly help me follow. So the presentation, you are defining an energy meter, and so if you can explain me energy meter, this would be a software algorithm. It would be a hardware that we are designing. Very briefly and generally, but to allow me to follow better.
Yeah, sure. So there is a need to actually have one common understanding and API to register such a hardware meter, because we currently stuck with software models. We don't have a mechanism in, for instance, DTPM or thermal to get this kind of meter from maybe existing drivers, which can be registered there already. But the vendors, they don't follow like those rules. And then if we can have like a one known standard and interface, then we can fix existing problems that we have. And yes,
the problem is limited to, say, non-Intel hardware, because on Intel we have already power meters in RAPO, which are architectural.
yes.
So they are exposed and they can be used.
For you probably don't use those algorithms, and yeah. But as I mentioned, we don't have a force to force our vendors to even use our firmware, which will actually allow to get reliable data from firmware about the energy, because of some legacy firmwares and different implementation of the chips.
Yeah, so my point is that for Intel x86 there already is an interface that can be used to measure power, energy in the RAPO SysFS, and that is also adjusted for security.
Yes, I will mention this. I will.
So that is. But I do realize that there are multiple architectures where there are no like architectural definitions of things like that. So
yes. So if we could agree on some common understanding and some requirements, also security, is from the security, then that would be good, at least for our world. For those devices and architectures, we don't fully control this environment, but there might be already some hardware meters on those platforms. Okay, any other questions? No, okay, I will continue. So those are some common requirements, I hope, that we could discuss. I would propose that there is some easy access to this meter, and I believe that's the energy meter. So if you have a power meter, then we might have such a thing like conversion from the power to energy, because when we know the time, then we can convert that. It doesn't have to be super high resolution. One of the reasons is this security reason, but just we have to agree what kind of resolution we need for what purpose, and that might be just registered as this new device and then could be reused. So easy configuration for this meter. So ideally it can work from the beginning. I remember those times when the thermal had some issues because of the boot time registration and all this hassle, where it can be used, or so I hope this could be solved as well, this configuration and registration. And ideally we could expose this to the user space when we comply with the security concerns, so other distro tools can use it, something like PowerTop. And also I would like to have the mechanism that we can use for tracing, so mapping, actually matching the time when we actually measure and what is going on with other subsystems in the kernel, such as a scheduler, so we can match this power delta values or energy values with the tasks that they are there currently running, and we can study this. Here's one example of such an energy meter. As you can see on the y-axis, I call it energy, but this is really the milliseconds. So this is kind of derived energy from the power meter. And as you can see, this is monotonically increasing. Some of the values, they are read few times the same from this device. And this could be good or bad. It depends what we agree. But that makes some noise on this security related stuff. So as far as you agree with this kind of mechanism, in the time plot, this is roughly 50 milliseconds, which is good enough to see what is going on, as you could see on this plot with the Geekbench then I think that should be okay-ish. Maybe 10 milliseconds would be good, maybe 1 millisecond would be good. Yeah, we can test that and we can discuss this security concern. But the main idea is that we have kind of a monotonically increasing counter. So if you count this energy and the value will never be low, then you can derive quite useful information after you do during the post-processing, after you record. Yeah, and we actually use that quite heavily in our validations. We run different experiments, and that was quite a good idea to have this in the trace. This is the design proposal for such a device, and I put a power cap framework here because we roughly discussed this with Rafael and Daniel. I already see some idea where we can put this. The plot that I showed you was with the energy model framework, but that might not be the right framework, especially in context of this requirement to expose into the user space in the standardized path, which is actually there. So if you go to PowerCap, you would see a file node called energy microjoule. It is just there, so we could reuse the path. If we need some middleware also knowing the energy, so we could reuse that framework, in my opinion, because the energy model framework doesn't have sysfs control at all. There is only debugfs. So as you can see, in the middle of the bottom, we have this physical device which already registered with some driver to this IIO, and it actually registers to this new energy meter interface to the power cap. And that is actually shared to two components, the DTPM that Daniel is maintaining and the IPA time maintaining. And this is actually quite easy and understood plot, in my opinion. So every vendor could actually deploy such a thing. Yes, Daniel?
Yes, I think it will make more sense to have a cooling device directly interacting with the power information from DTPM abstracted. So we don't have to, we can have a generic cooling device, power-based cooling device.
Yes.
Without using the energy meter, but using DTPM directly.
Directly, yeah.
So we have basically get and set power.
Yeah.
And then we have the backend.
Yeah.
So that could be the energy meter or whatever.
Yeah, I remember that discussion. Yes, you told me that idea. Yeah, I'm open to that idea as well.
And in the power cap,
yes,
indeed there is this energy file, but how do you set up the sampling?
Yeah, so this is something where we have to discuss during this registration period. So either we set the requirement from this client, which is the DTPM, for instance, that I would like to have resolution or update time for this monotonically increasing counter every, let's say, 20 milliseconds or 10 milliseconds. And then that will be propagated to this driver to give me that data.
And that won't be the backend configuration directly. So when you load, for example, the module, then you have this info. Well, when you, not the module, but when you load the module which register for the DTPM as a backend, then it can set up itself with the right.
Could be, yes.
So we don't have to extend the power cap framework.
Yeah, makes sense.
Yeah,
makes sense as well. Yeah, so that's pretty flexible, I would say, for now. This is just a proposal of the design, and yeah, we can do this a bit later. Yeah, this is the continuation of this usage and maintenance. So yeah, we will have to agree how we could configure, how we will maintain this, what are the requirements for those drivers which would like to hook into this new API. I would like to have something maybe inside that framework, the power cap, which is able to record the tracing for us. So if I would like to have the record of the energy values then maybe a worker thread firing up every like 20 milliseconds and will store the data into the trace file. Something like this would be useful. So I would like to have such a worker locally somewhere, which will just read this driver callback and store in the trace buffer, because that's kind of a lightweight way to record that. And that would be useful as well for me when I contact our partners and I ask for some traces. And quite often, yeah, if you don't have in one common standardized way to get the measurements, then that's a bit hard. Yes, Martin?
So have you any thoughts about what energy meters you would expect to be available on the platform and what parts of the system you're actually measuring? I think that's a very fundamental question that needs to be answered first, because I don't think you can assume that you have an energy counter that exactly maps your thermal zone or whatever you want to tie it up against. How do we express that? I mean, you know, from Pixel 6, the littles you measure together with the level 3 cache, for example. How do you express that in a way that tools and users can figure out that you're actually just not measuring the CPUs, you might be measuring other stuff together with it?
Tough question. Well, if we, let's say if we use this for the thermal control, and the power actually consumed by the littles is affected by the DSU as well, we could probably just aggregate those two and live with that. The harder requirement would be if you would like to have a fine-grained control per one core of your power. So you would like to know how much energy you consume for each core while you run some workload. And this is really tough because I haven't seen such a hardware that can give you per core information about the energy. The most likely you can measure the power rail.
The reason why the energy meter is exposed under the RAPL interface for Intel systems is because it then is clear what this energy meter actually the scope of it is clear, because it's the same as the scope of the control interface in RAPL. So it is for CPU, then the energy meter is for a CPU. If it's a package, then the energy meter is for a package. And then this way you get that information like from the interface automatically.
Yeah, so this is based on the hierarchy that you build in the software, because this is aligned with the hardware.
But so it needs to be kind of like a control zone that you use this energy meter for. So, you know, in power capping is kind of easy because the control interface applies to a certain piece of a chip, right? Like, and then you measure energy for it in order to control it.
Yes.
Right. So I think that this concept has to be extended, because then you need to define a zone of control to which you want to somehow, I don't know, power cap or do some thermal control of something like that, and then the energy meter is related to that zone.
Yes.
And this gives you the information about what you measure, basically. But because that's where the question goes, I believe.
Yeah. So this would be for the part of configuration and registration of these meters, and how we define this boundaries and hierarchy, maybe.
Sorry.
Yes.
Do you know with the sensor you have, these energy meters, power meters, if you have the capability to, for example, say you put the limit and then you get notification when you reach the limit.
Okay.
Not the limit, but the threshold, to say, okay, like a 3 point, but for power or energy. Do you know the energy is able to do that?
For this particular that we use, no.
No.
But for the others, it would be possible to get, but it depends on the hardware and the driver. Yes.
Okay, so maybe the polling plus periodic logging plus sending notification when we cross can be folded in a single timer instead of having a lot of each of them working straight for periodic logging, polling to get periodically the value. We can fold that into a single callback.
Yeah, possible.
Yeah.
Yeah, we would have to discuss those details, and I will make some notes. Yeah. I have 5 minutes. Let me check if I will finish. Yeah, hopefully. So yeah, just as like a summary, we would like to expose these energy values to the middleware to make some better decisions. We would like to also use this for tracing and recording in that trace file these energy values, so we can do the post analysis. Those are the results that you might find on mailing list or on some traces that we share. And one of the last thing, yeah, this is the snapshot from Lisa, where we can actually see 4 plots. There is one more extra at the bottom comparing to the one that you have seen previously. There is a temperature of the big core, then the middle plot, that's the big CPU cooling state. Then there is the power usage in time. And the last one, this is an activation of the single-threaded task during the Geekbench. So if we have such data, then we can discuss about some details. Improvements for the EAS that we discussed yesterday, or improvements for the youth lamp. But we have to be like aligned and use the standardized ways of analyzing the data, which we currently don't have from phones. And even if that interface won't be used for controlling the thermal or controlling the power situation, we still can use this for post-processing analysis from any phone. So that's one of the main ideas.
The kernel is not a very suitable place for power control because it's too slow to react, because it's not even a scheduler tick resolution, it's a scheduler, it's a resolution of a kernel thread.
Well, yes, I understand.
It's scheduled and do everything. So it can be used for what you have initially proposed. So it can be used for collecting data on.
Yes, this is for the future generation.
Things like that, but it cannot be used without hardware support. It cannot be used for actual control.
Not fully true, because we currently have devices which rely on IPA, rely on energy model. So those are legacy, but they have the
thermal control and not power control.
Thermal control, yes.
Yeah, so I'm talking about power control, which is a different time scale.
True.
And by orders of magnitude.
Yeah, but those are different worlds, Rafael. So we already have some legacy devices over there which use the thermal control, those loops.
The thermal control is, is covered by the thermal framework, whereas this is something else.
Well, so for the thermal framework, we don't have reliable input about power usage. And that was one of the points that I made. So, well, I understand Intel platform, but
that, okay, so we are talking about different things now. So we are talking about providing input to the thermal framework, and at the same time, you are talking about exposing this to user space.
Yes, for future generation processors.
These are separate problems.
True, but I wanted to propose the big scope, Rafael, for some legacy software and from some legacy devices which are there, and for some modern, which we don't fully control. As you could see, we will get more aggressive CPUs. This is not for them to control them. This is more about the post-processing and optimizing the algorithms on top. So for instance, if we share the plots with Vincent or with other guys who review
so my point is basically that we need to first agree on the goal, and then and then talk about how to get to it, because it's not clear to me what the goal is at this point.
Okay. Well, we can catch up later. But that's the current situation of this hardware plus software design. Yes, question?
Yes. For this meter, for this specification that you're working on, we talked about you touched on security, and you mentioned the time resolution at which you want to like allow this metering. I was thinking, is in scope the resolution of the wattage measuring? ARM could be a server, could be a phone. So I don't know, do you want to do milliwatt as well as watt, or your spec will not even care about that? Or will you measure watt? Or, for example, I've heard some time ago that RAPL does not directly measure watt, but what it actually measures is current, so ampere. And is that something that your specification will worry about, or is something that you consider out of the perimeter that you are designing?
So first, I would like to have like a standard metric. So we would stick with microjoules. So that would be the resolution of your measurement. But if the meter would be capable to actually measure microjoules, or maybe 10 of microjoule or 100 microjoule, and it will increase by this value, that's up to the vendor and his concern about security. And also the other domain, so the time domain, how often you will get this value. So those two domains, the time and the resolution in time, that's up to whatever you decide that is safe to expose to the kernel and maybe to the user space further. But then you can get actually any phone, if that phone will plumb in this driver to this framework, then you could easily trace it. And you can reason about not only one phone that we have now or two phones, but you can probably test different phones, and then you can just record the trace for them and see what is going on with the solution there. So that's the main scope for those modern processors. For those olders, the goal is to actually have a bit better thermal control. If they rely on the thermal in IPA, then the problem of the estimating power is there by the software under or overshooting. So those two goals, but we have those requirements that we have to think about. Yes? Okay. Okay, thanks, Yuri.
Just one question. Have you measured how much energy you're consuming to measure the energy?
Well, so it's like a problem of how much waste is on your PMIC, because the efficiency of the PMIC is not 100%. So you drop some energy there in order to make a new voltage for your CPU in the DVFS.
No, I mean, not only on the PMIC level, but my understanding is that you have a thread waking up regularly to monitor that.
Okay.
So your CPU, you have one CPU waking up and running to monitor. So have you estimated how it's, which kind of noise that's?
Well, yes. So we have two implementations for that, and we have seen this. First implementation I have made, it was waking up this worker thread and collecting the straight data from the structures and logging to the trace buffer. The second one that we officially published in LISA module, that opens a file system, sysfs, which reads from the sysfs, parses the data, maps them to the integer or unsigned, stores into the trace buffer. That is moreover more energy consumed. And I would like to avoid this actually. So if it would be like this 5 microsecond thread, we just wake up, read the data by the callback, and then store it, then that would be preferred way. We currently in LISA have the hard part. So opening the file system module and then parsing strings. So this is not the lightweight way. But yes, this is a good question. So I've been trying this one and that one. And I can see the difference. It's tiny, but there is some. The next one. Okay, thank you. There are no other questions. I will have